Swayam Prabha. Digital India. Educated India.
In the last lectures we have seen one dimensional boundary value problems like bar under axial deformation, and also while we are solving 3-dimensional frames we have seen differential equations, differential equation for torsional problem. So these two kinds of differential equations for these two problems, that is bar under axial deformation and also bar under torsion, the governing differential equation falls under the category of one dimensional boundary value problem. So in today's class what we will be doing is we will be actually looking at a more general one dimensional boundary value problem, and subjected to some boundary conditions which includes both essential and natural boundary conditions, and how to derive finite element equations using linear element. And before doing that we will first derive equivalent variational functional for this one dimensional boundary value problem using Rayleigh method, and whatever the procedure that we followed earlier when we are solving other problems in the earlier lectures, the same procedure you will be following as far as Rayleigh method is concerned or Rayleigh procedure is concerned, and also this general one dimensional boundary value problem can also be solved using Galerkin method, which we will be looking later when we take instead of linear element, when we deal with higher order elements like quadratic elements in the later lectures. But in today's class we will be using Rayleigh method for solving one dimensional boundary value problem. Now let us look at what is this one dimensional general one dimensional boundary value problem. A large class of practical one dimensional problems is governed by a linear second order differential equation of the form. Here this is what we mean by a general one dimensional boundary value problem. So for a particular or for a specific problem, if you can identify what is this k, coefficient k and p and q, and so when we get the equations for this general one dimensional boundary value problem at those corresponding locations, you can substitute what is this k, p, q and get the equivalent element equations for that particular problem. So now let us look at this problem, which is linear second order differential equations, where k, x, px, qx are coefficients or coefficient functions, and t is some field variable, and t can be any problem dependent variable. And once we solve this general one dimensional boundary value problem, you will see application of this in heat flow problems and also lubrication problems and also in structural mechanics problems related to column buckling. So now this is the governing differential equation that we are taking, and the corresponding boundary conditions for this problem, appropriate boundary conditions for the problem are of the following form. If you see the problem statement, the domain goes from x0 to xl. So the boundary condition at x is equal to x0 is, if it is an essential boundary condition, it is t is equal to t0, where t is the field variable, a specified constant, or you can have natural boundary condition like this. Again here k naught, alpha naught, beta naught, or k naught is k value at x naught and alpha naught b naught are some specified constants. So you can have either of these boundary conditions specified at x is equal to x0 to solve the differential equation or the general one dimensional um, the governing equation that you have seen. These are the boundary conditions. Any of these essential or natural boundary condition can be specified at x is equal to x0. At x is equal to xl, t is equal to tl, a specified constant which is essential boundary condition, or natural boundary condition can also be specified where kl is k evaluated at x is equal to l, alpha l, beta l or some constants. So this is the problem definition. The differential equation is given, problem domain is given, x is going from x naught to xl, and the two boundary conditions or the boundary conditions at the two ends at x is equal to x0 and at x is equal to xl, either essential or natural boundary conditions may be specified. So this is what we assume, and with this we will start. So now before we derive the element equations using substituting finite element approximations, we need to arrive at if you are adopting Rayleigh-Ridge method, we need to derive equivalent functional. So the first step in deriving equivalent function is the given differential equation is multiplied with the variation of quantity that we are interested, integrated over the problem domain and equated to 0, and here the quantity that we are interested is in finding the field variable value. So t is what we are looking for. So the given differential equation needs to be multiplied with variation of t, integrated over the problem domain which goes from x naught to xl and it equated to 0. Derivation of variational functional for the boundary value problem follows the steps presented earlier in the earlier lectures. So multiplying the given differential equation by variation of t and integrating over the problem domain and equating it to 0, we get this is the first step, and now we need to identify higher order terms, and wherever higher order terms appear we will replace them with lower or as low as order possible by integration by parts. So here integrate first term by parts to reduce the order of differentiation, integrate first term by parts to reduce the order of differentiation. So when you do integration by parts on the first term, we get this equation, and you can see the terms inside the integral. Some of these can be further rewritten using the variational identities that we learnt in the earlier lectures. So from variational identities, k times derivative of t with respect to x, derivative of variation of t with respect to x can be written as variation of half k times derivative of t with respect to x square of that. Similarly p times t times variation of t can also be written as p times or variation of p over 2 t square. Q times variation of t can be written as variation of qt. So from the variation identities we get this, and now substituting these and multiplying by minus sign we get this equation, multiplying the entire equation by minus sign, we get this equation. And if you see the first two terms, they are related to the boundary conditions that are given, because k times derivative of t with respect to x at x is equal to xl is given, and also k times derivative of t with respect to x at x naught is also given. So from natural boundary conditions that are given, we have this equation, and also we have this equation from natural boundary condition that is specified at x is equal to xl. Substituting these boundary terms, into the boundary terms, we get variation of t times k times derivative of t with respect to x evaluated at x is equal to x naught. We can write like this, and also which can be further rewritten using variational identities. And we have the other boundary term, which can also be written in a similar manner, and also which can be rewritten using variational identities. So now substituting all this back into the equation, we can pull variational operator out. So the entire expression now is sum of variation of individual terms. So whatever is there there inside the square bracket, that is equivalent variational functional. So the appropriate functional for the general one dimensional boundary value problem is given by this. So using this functional and equations for a 2 node linear finite element, if a 2 node linear finite element is chosen for discretization, so using that and equations for 2 node finite element, a linear finite element can be derived. And here the rest of the derivation will be using Rayleigh-Ridge method. Rayleigh-Ridge method will be used for the derivation. Galerkin method can also be used to get the same equations without whatever equations that we are going to get using the Rayleigh-Ridge method. Similar equations can also be obtained using Galerkin method. So now we have the equivalent functional. So before we proceed further, we need to look at the finite element approximations of each of the terms that are appearing in the equivalent functional, how to express their approximation in terms of finite element shape functions and nodal values. We need to look into it. So linear finite element for general one dimensional boundary value problem, the procedure will be same even if you use higher order elements, which we will be looking at in the later lectures. A typical 2 node element for the boundary value problem is shown in figure below, having 2 nodes, node 1 at x1, node 2 at x2, length of the element being L, field variable value at node 1 is T1, field variable value at node 2 is T2, and the positive direction of the coordinate system x is also indicated in the figure. So, this is the typical 2 node element for the boundary value problem that we are going to solve. The unknown solution at the nodes is identified as T1 and T2. So, since we are taking a 2 node finite element having node 1 at x1 and node 2 at x2, the functional that we derived can be defined over this element like this. Functional defined over the element is as follows. So, x naught is replaced with x naught is replaced with x1, xl is replaced with x2, and also alpha naught beta naught are replaced with alpha 2 beta 2, sorry, alpha naught beta naught are replaced with alpha 1 beta 1, alpha L beta L are replaced with alpha 2 beta 2. So, here in this equation which you have seen, alpha 1 beta 1 and alpha 2 beta 2 are coefficients in the natural boundary conditions when they applied nodes, when applied to nodes 1 and 2 respectively, when natural boundary conditions are applied to nodes 1 and 2 respectively. And also it should be understood that the boundary terms in the functional are to be included possibly for the first and last element only. That will be more clearer when we are actually solving a problem. So, the term half alpha 1 t square plus beta 1 t evaluated at x1 would appear in the equations for element 1, assuming left to right element numbers only if a natural boundary condition is specified at x is equal to x naught. Similarly, the term half alpha to t square beta to t evaluated at x2 would appear in the equation for the last element only if natural boundary condition is specified at x is equal to xl. These points will be clearer once we solve a problem. For all other elements which are in between first element and last element, for all other elements integral term of the functional is the only one that is applicable. So, whatever the functional that we are defining over the element is more general. So, for some elements only the first boundary term and the integral may be possible, and for some cases, for some elements, second boundary term and integral term are only possible, and whereas for some other elements which are neither first element or last element, for such kind of elements only integral term of the functional is applicable. So, now we have functional defined over element, we need to substitute finite element approximation. So, we need to make the field variable approximation in terms of finite element, 2 node finite element, shape function and nodal values. So, the element x1 to x2, 2 node element x1 to x2 will be mapping onto s coordinate system, where s goes from -1 to 1, s is equal to -1 corresponds to x1, s is equal to 1 corresponds to x2. So, define a change of variable such that integration limits are from -1 to 1 instead of x1 to x2. So, the relation between the x coordinate system and s coordinate system is given by this equation, which can be easily derived using linear interpolation formula, which we already did in earlier lectures. So in this relation, note that x is equal to x1 gives s is equal to -1 and x is equal to x2 gives s is equal to 1, and the equation can be rearranged as shown in the slide, and we get the inverse relation between x and s. From the relation, first equation you have the relation between s and x, and rearranging it we get relationship between x and s, which can be taken after taking derivative on both sides, we obtain this, which can be rearranged such a way that ds over dx is equal to 2 over L. And if you see the functional, we have derivative of t with respect to x. So there we will be using this relation ds over dx. Using chain rule of differentiation, derivative of t with respect to x can be written as dt over ds, ds over dx. Just now we have seen ds over dx as 2 over L, where L is length of element. So the previous substituting whatever we have in the previous equation, that is ds over dx is equal to 2 over L, here we get what is shown there. So derivative of t with respect to x is 2 over L times derivative of t with respect to s. Also we know that for 2 node element, the linear trial solution in terms of finite element shape functions is given by this one, t as a function of s is n1 t1 times n2 t2, which can be written in a matrix and a vector form in this manner, and which can be compactly written as n transpose d. And from this we get what is derivative of t with respect to s. It can be easily verified. It is given by minus half half put in a matrix form multiplied by t1 t2 put in a vector form. So using this, if you multiply derivative of t with respect to s with 2 over length of element, we get derivative of t with respect to x, but that is what is shown here. Derivative of t with respect to x is derivative of t with respect to s times derivative of s with respect to x, and which can be compactly written as b transpose d, whereas b transpose is defined as minus 1 over L put in a matrix form, or it is a row matrix. So we have the field variable approximation in terms of nodal values and shape functions, and also derivative of t values, derivative of field variable with respect to x in terms of derivatives of finite element shape functions and the nodal values. So we need to substitute this trial solution and its derivative into the functional. Since t1 t2 are unknown, we have to arrange the terms carefully so that required integrations can be carried out in an orderly manner. So now we will take each term in the equivalent functional. So now let us consider the first term in the functional, and if you see the first term in the functional, square of first derivative of t with respect to x is appearing. So, derivative of t with respect to x, square of that can be written as derivative of t with respect to x transpose times derivative of t with respect to x, because derivative of t with respect to x is a scalar quantity. Square of a scalar can be written as scalar transpose scalar. So, using that logic we get this, we can write derivative of t with respect to x square in this manner, and we know that derivative of t with respect to x is b transpose d. So, substituting that we obtain this equation after carrying out the multiplications of b transpose. So, substituting this square of the first derivative of t with respect to x into the first term, the first term can therefore be evaluated as, this is the first term appearing in the equivalent functional, and now substituting derivative of t with respect to x square that in terms of finite element shape functions or derivative of finite element shape functions, which is d transpose b transpose d, and k is the coefficient, and we know that d, which is t1 t2, which are the nodal values, and they are not functions of spatial coordinates. So, d transpose and d can be taken out of the integral and defining kk as integral k times b transpose L over 2 ds integrated between -1 to 1, and carrying out the multiplication of b transpose. This can be further written in the way it is shown. And here the explicit integration is possible only if coefficient k is given as a function of x, and if k is constant over the element, then k can be taken out of the integral, and rest of the integration of rest of the terms can be carried out, and we get k divided by L times 1 minus 1 minus 1 1 as shown in the slide. So, the first term appearing in the equivalent functional after making substitution in terms of finite element shape functions and derivative of finite element shape functions, we get this, and here this equation, or this is valid only if k is constant over element. So, this is the first term simplification. Now, let us look at second term. Second term in integral can be evaluated in a similar manner, except that in the second term we have t square. So, t square, t is again field variable, it is a scalar quantity. T square can be written as t transpose t, t is n transpose d. So, t transpose is d transpose n. So, t transpose t is t transpose n transpose d, and after making substitution of d and n values and simplifying, we get this equation. Making substitution of this t square into the second term, appearing in the equivalent functional, we get this equation. Here defining Kp as integral minus 1 to 1 minus p n transpose times L over 2 ds, defining that as Kp, we can compactly write this in this form. Again here d is being a vector of nodal values, it can be taken out of the integral. So this simplification is possible because of that. And now looking at Kp, where Kp is defined like this. Here also, unless explicitly p is given as a function of x, integration is not possible, but for a specific case where p is constant over an element, we can take p out of the integral and we can simplify this, simplify each of the terms appearing in the matrix, that is carrying out integration of each of the terms between minus 1 to 1. If p is constant over an element, then Kp can be simplified to this. So we have simplified the first term and the second term appearing in the equivalent functional. Well, now we need to look at third term. Third term in the functional can be evaluated as follows, substituting t value in terms of finite element shape functions, which is n transpose d, and rearranging it, since d is not a function of spatial coordinate, we can rearrange it as rq transpose d, where rq is defined as q integral minus 1 to 1 q n transpose L over 2 ds. If rq transpose is defined in that manner, rq can be written as integral minus 1 to 1 minus 1 to 1 q n q times n L over 2 ds, substituting finite element shape function values. N transpose is defined as 1 minus s over 2 1 plus s over 2. So n is defined as, put in a the same thing, put in a column vector form, and again here if q is constant, we can take q out of the integral, carry out the integration, and we get this rq is equal to q L over 2 q L over 2 put in a column vector form. So now all the terms inside the integral, inside the equivalent functional, or all the terms appearing in the inside the integral of equivalent functional are evaluated, and only the natural boundary condition terms are remaining. We will look into those things, noting that t evaluated at x1 is equal to t1, t evaluated at x2 is equal to t2. The boundary terms can be written in this manner. And in order to combine these boundary terms in the rest of the matrices, they are rearranged, or they are arranged in a matrix form So these boundary terms are arranged in a matrix form, in this manner, and also the other term is arranged like this, where k alpha and r beta are defined like this. So, now all the terms in the equivalent functional we express them in matrix form, and combining all the terms together, the equivalent functional can be written in this manner. And now we need to apply the stationarity condition. Variation of I is equal to 0 is possible only when partial derivative of I with respect to the unknown parameters, which is here nothing but d vector. So, partial derivative of I with respect to d is the stationarity condition. Applying that condition, we get this equation, which can be compactly written as kd equal to r, where k is defined as sum of kk, kp and k alpha, and making substitution of kk, kp, k alpha, we get this, and also r is defined as rq plus r beta. And please note that this equation is obtained by assuming k is constant, k, p, q are constants over element, and note that alpha and beta terms result from natural boundary conditions specified at the ends. And if, for example, a natural boundary condition is specified only at node 1 of an element, then alpha 1 beta 1 terms must come from natural boundary conditions, and alpha 2 beta 2 are going to be 0. Also remember that the explicit expressions for element equations assume that k, p, q to be constant over an element. If these values are not constant, then one can determine new element matrices by carrying out the integration, keeping k, p, q inside the integrals and integrating and on carrying out the integrations, or the solution domain can be divided into large number of elements, and over each element an average value of these coefficients of these parameters k, p, q can be used, and then we can use these equations. But this kind of approximation is going to be in addition to the already approximation that we are using for finite element discretization, which is linear element. So, there may be some error in the solution, however, as the number of elements increases, this error due to approximation becomes negligible. So, this is what is mentioned. So, now what we will be doing is we will be taking an application of this general one dimensional boundary value problem, which is one dimensional heat flow. So, basically what we did is we derived the element equations for a linear finite element for a general one dimensional boundary value problem subjected to both essential boundary condition, natural boundary conditions, and for a specific problem related to any application, what we need to do is we need to identify what are these coefficients k, p, q, and also from the boundary conditions we can identify what are the alphas and betas, and we can directly use the element equations that we derived based on linear finite element approximation, and we can plug in into these and we can get the element equations for corresponding problem, which will be very advantageous. So now let us look at application, steady state heat conduction. So the one dimensional steady state heat conduction problem without convection is governed by the following differential equation, where Kxx is thermal conductivity in x direction. Please note that this is one dimensional problem and the units of Kxx are given, and temperature T is the temperature, field variable now is temperature, field variable which we have in general one dimensional boundary value problem is now temperature, and Q is heat generated, internal heat source per unit volume, units are given. So this is a linear second order differential equation, and which is similar to what we have seen general one dimensional boundary value problem, the differential equation corresponding to general one dimensional boundary value problem. So now let us look at what are the boundary conditions. The appropriate boundary condition at the ends are one of the following two forms: essential boundary condition or natural boundary condition. So what we need to do is we need to make a comparison between the this differential equation and these boundary conditions and the differential equation and boundary condition that we have taken for getting the element equations for one dimensional general one dimensional boundary value problem. So the finite element equation for heat flow problem are obtained by first looking at the similarities between the governing differential equation and the one dimensional general boundary value problem that we already looked at, and we can make a table like this. What is the variable in general one dimensional boundary value problem and corresponding variable in the heat conduction problem, and what the corresponding variable in the heat conduction problems actually stands for. We can make a table like this. So this table helps us, we already have the element equations assuming linear finite element and also a linear finite element, and we have the element equation for general one dimensional boundary value problem. So with this table we can actually directly get the substitute the corresponding coefficients values and get the element equations for heat conduction problem or heat flow problem. So looking at the table, we can get finite element equation for heat flow problem simply by substituting heat flow parameters into finite element equations for general boundary value problem. So doing that, we get this element equations. So, for one linear finite element, for this problem, these are the element equations. So, if you have more number of elements, for each of the element we need to get equations based on this, and then we can assemble the global equation system, apply the boundary conditions and solve for the nodal unknowns. So, in this equation, element equation, T1 T2 are the nodal temperatures, because now T here T in the general boundary value problem, which is field variable, now is temperature. So, T1 T2 are the nodal temperatures, Q1 Q2 are the specified heat flows or heat flux, and note these equations are valid when Kxx and Q are assumed constant over an element, because that is what we assumed when we are actually deriving element equations for general boundary value problem. So, now to get more understanding, let us take an example and solve it. As shown in figure below, figure is shown there. The inside of a 1 meter thick wall is maintained at a constant temperature of 200 degrees centigrade, while the outside is insulated. There is a uniform heat source inside generating heat, which is given Q value, and thermal conductivity Kxx is given, and we need to find temperature distribution in the wall, and a schematic showing the wall and the inside temperature and outside insulation is shown. The thickness of wall is 1 meter, and assuming the wall is very high, it is possible to model a unit slice of wall as one dimensional problem. So, this is the problem. So, assuming the wall is very high, using a one dimensional model, we can model unit slice of wall no heat can flow from top and bottom surfaces, bottom faces of the model. So, this is what the schematic shows the meaning of the statement no heat can flow from the top and bottom faces of the model, and the entire wall thickness is discretized using 4 elements. So, each element and 4 elements of equal length. So, each element length of each element is 1/4 meter or 0.25 meters, and 4 elements are taken, each element has 2 nodes, and the values of temperature at each of these nodes is also indicated in the figure T1, T2, T3, T4, T5. And now the boundary conditions are T at x is equal to 0 is 200, and because of insulation heat flow is 0 at x is equal to 1, and here x is equal to 0 corresponds to node 1, x is equal to 1 meter corresponds to node 5. So, T1 is equal to 200, Q5 is equal to 0, So, substituting all these things into the element equations, since all the elements are of equal length, all elements are identical and have same element equations which are shown there. Which can be simplified. So, this is the equations, these are the element equations for one element, and all elements will have similar kind of or same identical equations. So, assembling using this one element equations, we can assemble equations for all the 4 elements. Assembling equations for 4 elements, we get this one, and now making substitution that T1 is equal to 200 and Q5 is equal to 0, and doing partitioning of matrices and rearranging, imposing the boundary conditions and ignoring the first equation, we get this, and rearranging this equation we can solve for T2, T3, T4 and T5. And the solution of this equation system is this: T2 is equal to 203.5 degrees centigrade, T3 is equal to 206, T4 is equal to 207.5, T5 is equal to 208, and T1 is already given, which is the boundary condition, essential boundary condition given, that is T1 is equal to 200. So, now we can plot the solution. Solution is plotted in the figure below. So, this gives us heat conduction through the thickness of wall. So, this is how the element equations that we developed for general one dimensional boundary value problem can be used for solving some of the problems, and this is one application, and in the next class we will be looking at some more applications.